Hi, I'm Amit. I'm working on deep learning based convolutional neural networks for the purpose of iso-edge polygon detection. In this poster, I'm going to show you our findings when we implemented image augmentation techniques on top of the deep learning convolutional neural networks. So let's start. In our research, we target on detecting iso-edge polygons from very high resolution satellite imagery on a pixel level. That means we assign levels to each of the pixels in the satellite image. This task is called semantic segmentation in computer vision. For this task, we use deep learning based convolutional neural networks, also known as deep learning CNNs. The reason for using deep learning CNNs is that these networks are really good at semantic segmentation. However, before using these networks, we need to train these models. For training these networks, we need hand annotated images, in fact a lot of them. For annotating the images, this is a very time consuming and labor intensive task. What we did in this project is we tried to provide a data space solution to inflate the number of training images by using image augmentation techniques. I will discuss more on image augmentation techniques later, but first let me tell you our goal for the project. The objective of this project is to understand the effect of image augmentation on deep learning convolutional neural network algorithms. Before jumping into the augmentation methods, let me discuss about the iso-edge polygons in Arctic tundra. Tundra is a major zone of treeless level or rolling ground found in cold regions like the north of the Arctic Circle. Tundra occupies a huge portion of the continuous permafrost or permanently frozen grounds in the Arctic region. One of the most common features of this region is iso-edge. Iso-edges are responsible for the polygonal shape of Arctic tundra region. For this study, we have collected 7 satellite images from the Arctic region. Those are from Alaska, Canada, Russia. Since the satellite images are huge in size, we prepared smaller tiles as needed for the deep learning convolutional neural networks. Then we hand annotated iso-edge polygons from these tiles. We prepared 3 datasets from these image tiles. One for training the model, one for validation of the model when the model is being trained, and the other is for testing the model performance. We already know that semantic segmentation is the task of adding labels to each of the pixels. Now let's see how our deep learning convolutional neural network model works. The name of our deep learning CNN is mask RCNN. This network is a little bit complicated and has a lot of blocks inside it. There is a CNN backbone that finds the regions with iso-edge polygons. After that, there are a couple more blocks, fully connected layers, connected sequentially to predict the class of the detected iso-edge polygons, to find out the bounding box, as well as to generate masks of these polygons. Now let's talk about image augmentation methods. We have used 4 types of image augmentation methods. Each of these types include a couple more techniques. What you can see in this figure is the techniques that we have used, such as hue, saturation, cropping, flipping, noise injection, and finally combinations of multiple augmentation methods. Let's see how the augmented images look like. We get a zoomed version of image when we apply crop method. We get flipped or rotated images based on the augmentation methods applied. In this figure, we show sample images of every augmentation method that we tried in this project. Once we have our augmented images ready, we are ready to train our models. Here is a figure to compare our workflow before and after implementing augmentation methods. So you can see that the augmentation methods inflate the total number of input images that are sent to the mask RCNN model. Once we are done with the deep learning convolutional neural network model interfacing, we get our outputs based on our input tiles. Then we stitch these tiles or outputs together and prepare the final map. We prepared outputs from all the augmentation methods as well as some combinations of different augmentation methods. If we overlay those outputs on top of the original image, those look like this figure. Polygons are marked in different colors for differentiating from each other. We can see that some augmentation methods such as flip, hue saturation, combinations of multiple models or methods, they did really well in terms of detecting polygons, while some could not detect polygons. Once we had our segmented images, we tried to prepare a bar graph to show the accuracy of different augmentation methods. As you can see, the mask RCN model without any augmentation method had an accuracy of around 64%. Some augmentation methods did really well and boosted up the accuracy. The best accuracy was found by the combination of top 7 augmentation methods, and that was roughly around 79%. That means 14.9% increase from the base model. We have also prepared a bar graph with the mean average precision values of different augmentation methods. The base model had a precision of around 63%. Then with the combination of top 7 methods, we found an increase of 15.4% in the precision, making the precision value nearly about 80%. We can see from the accuracy and the precision plots that some of the methods, such as rotations, they didn't really perform well. To understand the reason behind this, we plotted the probability density function and the cumulative distribution functions from 3 samples. One for the original image, one for a good augmentation method such as the salt and pepper noise, and one for a poorly performing method such as the rotation 60 degrees. Then we see that for the good augmentation method, the distribution plots look almost identical to the original image. However, the rotation 60 degree method, the distribution is very different from the original image and reportedly affected the model performance. Now let me conclude. We have found that augmentation methods can boost the accuracy and precision by a good margin. However, we have a lot more augmentation methods to be tried in our future works. Moreover, we should try changing the CNN backbone of the mask CNN model that we used. Perhaps we should try other deep learning CNN models such as UNet, DeepLab, Solo in our future works. So that marks the end of this presentation. Thank you everyone for your patience.